In this episode of KubeFM, I'm joined by Brian Donelan, lead software engineer at JPMorgan Chase. We dive into a side project he wrote about, teaching Kubernetes to autoscale based on whether his MacBook is open or closed. Pretty cool, right? By wiring screen lock events into CloudWatch, KEDA, and Karpenter, Brian built a system that cuts costs by scaling pods and nodes all the way down when he's not using them. What starts as a clever hack for saving money becomes a bigger conversation about event-driven elasticity, sustainability, and how developers can rethink the signals they use to scale workloads. Brian also shares how this approach could extend beyond personal projects into financial services, e-commerce, and other industries where leading indicators can make all the difference. We're excited to partner with TestKube for today's episode. Testing applications in Kubernetes doesn't have to be complicated or slow. TestKube is your go-to platform for cloud-native continuous testing. With TestKube, you can effortlessly orchestrate, scale, and automate tests right within Kubernetes, catching issues early and deploying with confidence. Try it out today and see why engineering teams trust TestKube to keep their testing simple and scalable. Visit testkube.io to get started. Now, let's get into the episode. Brian, welcome to KubeFM. What are 3 emerging Kubernetes tools that you are keeping an eye on?
Thanks, Bart. Well, first and foremost, I like to follow the Cloud Native Computing Foundation projects. 3 that I'm presently interested in are, first, Kepton. I know a lot of folks spend a lot of time and effort on their release trains. Kepton seems like a good solution that could help with deployment observability, evaluations, and tasks. Second, the operator framework. As you know, operators are an extension point into Kubernetes that allow you to write custom code to manage custom resources. I was earlier this year writing an operator for work to manage some aspects of a vendor product we run, and I found it fascinating. Third, Cilium and the eBPF stack. In the past at work, we used Calico as our container networking interface in Kubernetes, but we're looking at switching to Cilium soon. Cilium offers lower latency by bypassing IP tables in favor of extended Berkeley packet filter, and security benefits enabled by eBPF.
So for folks who don't know you, Brian, can you tell us what do you do and who do you work for?
Sure, Bart. So my story begins when I was 3 years old and asked for an extension cord for my birthday. I wanted to use the extension cord to figure out how the vacuum cleaner worked because I was afraid of the loud noise it made, but so curious about the device. So my parents knew from a young age that I was a bit of a dork, and by the time I was in 2nd grade, I was getting QBasic programming books from the library and reading PC World magazine cover to cover. Today, I work for JPMorgan Chase as a lead software engineer in the global banking platform. For probably the last 60 years, the bank has hosted most of the ledgers that serve as the core of the bank on mainframe hardware, and we're working on rewriting these legacy applications to be cloud native, running on Kubernetes and AWS.
And how did you get into cloud native?
In 2017 or so, I took an Udemy course on Kubernetes. At that time, I had just transitioned from a Java development role into a DevOps role, following a mentor of mine. The course on Kubernetes really captivated my attention, and I started playing with Minikube quite a bit. The team I was on at that time became early adopters of Kubernetes in the bank, back just as AWS EKS was getting started, back in the Kubernetes v 1.9 days or so, and we had an opportunity to evangelize Kubernetes and container-based development throughout the firm, which was really exciting. The bank was slow to adopt cloud at that time, though. Our CEO felt that cloud was akin to outsourcing IT, which he had seen fail dramatically in the past. He wanted soldiers, not mercenaries, so to speak. I grew frustrated with the slow progression of cloud, sensing it to be the future, and left to go to the aviation firm NetJets, where I got to work on a wide variety of AWS technology on cutting-edge applications and attend reInvent for the first time, which I loved.
And what were you before cloud native?
So I studied mechanical engineering at Vanderbilt University for undergrad, but many of my internships had strong elements of software engineering, or at least strongly IT adjacent. I quickly had an awakening that I liked software better than mechanical, not just because I was happier away from oil rigs or an automotive manufacturing line, where many of my classmates would begin careers. I found with software, you could rapidly develop new solutions and see them take on a life of their own, while mechanical had a longer time horizon to it. I finished my degree, but began aiming towards software. Once there, I did a mix of development, mostly Python, JavaScript, and Java, and sysops work, learning my way around a Linux command line. These skills were invaluable for my future career, but the mechanical engineering problem-solving mindset, the ability to deconstruct a system into its component parts and reason about them, continues to serve me today.
Now, the Kubernetes ecosystem and the cloud native ecosystem as well, they move very quickly. How do you stay updated? What resources do you use to know what's going on?
Yeah, great question. I think work is one resource. We have a central technology organization in the bank, which is constantly publicizing new technologies available for consumption, in addition to conversations and knowledge sharing with coworkers. The official Kubernetes blog is another great resource. For instance, I was recently reading about the Gateway API inference extension for routing inference traffic to large language model pods. The explanations were great, and the diagrams succinctly gave me a grasp of the concept. Another is the Code Report YouTube series by Fireship. I find these videos quite entertaining and informative about the latest developments in technology.
If you could go back in time and share one career tip with your younger self, what would it be?
I think it would be to spend more time on side projects. Side projects are a great resource because you can pick applications of technology that are very interesting to you and see where it takes you.
As part of our monthly content discovery, we found an article that you wrote titled "Goodbye Wasted Compute: How I Taught Kubernetes to Autoscale with My MacBook Screen Lock." So we want to dive into this a little bit more in with the following questions. You wrote about a fascinating approach to reducing Kubernetes costs by connecting your MacBook Screen Lock to cluster autoscaling. What problems were you trying to solve with this unusual solution?
Yeah, I was scratching around on a side project this spring and needed to run a handful of web services. These services I would normally have run directly on my MacBook, but they were too resource intensive for my hardware. The easiest thing to do was to run them in the cloud. That would, of course, entail hourly costs, which I was eager to minimize. I thought, these services are just an extension of my MacBook. No one else will use them. So can I find an automated way to turn them off when I close my laptop so I don't forget, leave them running, and rack up a larger than necessary bill? I think it's a problem that almost anyone who uses the cloud can relate to. In fact, there's a joke. A software engineer rubs a lamp and a genie appears. The genie says he'll grant the engineer $1 billion, but only if they can spend $100 million in a single month with 3 rules. You can't gift it away, you can't gamble with it, and you can't throw it away. The software engineer responds, well, can I use the cloud? And the genie responds, okay, there are 4 rules. In my professional work, this has certainly been borne out too. We were working on a greenfield application, moving fast, and the initial sizing of, for example, our managed streaming Kafka cluster was done based on an engineering assumption. Now, Kafka broker sizing is driven predominantly by the network traffic throughput at the brokers. Once the cluster is built and serving production level loads for a while, you can look at the data and see if you're oversized. When I got time to write a script to scrape actual CloudWatch metrics for that network throughput from 24 AWS accounts, I found we were overpaying by $500,000 each year, spread across the 24 environments. The lesson to me is that it takes equal parts discipline and automation to keep cloud bills in check.
In your article, you mention Werner Vogel's frugal architect keynote and the concept of elasticity in cloud computing. How does your screen lock solution embody those principles?
Well, traditionally, Kubernetes has scaled pods with horizontal pod autoscaler. Horizontal pod autoscaler is driven by metrics like CPU consumption and memory consumption of the pods. There's 2 problems with this. First, they aren't always the best proxies for demand. I've seen a number of event-driven workloads where the bottleneck is the network card, not the CPU or RAM. Second, metrics like these, and HPA more broadly, react more slowly than event-based triggers like incoming HTTP requests. Because of this, in the past, AWS Lambda, the function as a service offering where you bring your code and the cloud provider brings all the infrastructure underneath needed to run it, has been viewed by some as more elastic than Kubernetes. Lambda can spin up a new instance on the order of milliseconds to seconds. Kubernetes, on the other hand, to spin up a new instance, needs to first schedule the container, wait for the container image to pull, wait for any startup scripts and probes to clear, possibly even provision a whole new node if no existing capacity is available. My screen lock solution embodies the principle of elasticity because it allows me to scale apps up and down based on a leading indicator of whether I might want to use the apps or not, a metric indicating whether my laptop is closed or not. Which brings us to the frugal architect. Vogels lays down a series of laws for building cost-aware, sustainable architectures. His third law is architecting is a series of trade-offs. He says, cost, resilience, and performance are non-functional requirements that are often at tension with each other. I firmly believe and agree with these principles. That said, I believe the screen lock solution fits neatly into a niche space. The apps I'm hosting are only for my consumption, so scaling them down when I'm away from my laptop doesn't cause service degradation. It doesn't represent a trade-off by virtue of how unique the problem is. If I were serving tens or hundreds of users, I might look for other leading indicators of demand, as opposed to the lagging indicators demand we spoke about earlier, which might be CPU and memory. If I were serving tens or hundreds of users, I might perhaps even run a time series forecasting ML algorithm based on historical data as a first pass for scaling decisions.
Now, let's dive into your ingenious architecture. How does a MacBook screen lock event actually trigger Kubernetes pods to scale down?
Well, it all starts with the macOS daemon, meaning a background process. This process runs continuously on the developer's laptop, and so long as the laptop has internet connection, uses the AWS Software Development Kit for Swift to make API calls to put metric data for CloudWatch. This creates a Boolean value, 0 for locked, 1 for unlocked, and no value if there's no internet on the development machine, which stores in the cloud the time series of the state of the development workstation. Once this time series data is in the cloud, we can access it from anywhere, including from our Kubernetes cluster. So from there, the Kubernetes event-driven autoscaler will pull or query every 60 seconds on a loop to see what the value is currently. In our KEDA scaled object manifest, we define the properties for how we want our deployments to scale based on the events KEDA observes. Here we set min replica count to 0 and max replica count to 1, so KEDA will scale our deployment up when the Boolean value is 1 for unlocked, and down when the Boolean value is 0 for locked, or for no data, for no internet on the development box. But how does Kubernetes know to scale in the nodes when we scale down the pods? Well, that's where Karpenter comes in. We get Karpenter automatically by selecting EKS Auto Mode, where AWS provides Karpenter as a service. Karpenter is a just-in-time autoscaler for Kubernetes nodes and comes with a feature called consolidation, where nodes that are underutilized are purged once a properly sized replacement node is brought online, if applicable. So that's the whole flow. The macOS daemon sends metrics to CloudWatch. KEDA checks CloudWatch once a minute and scales the pods appropriately, which by virtue of Karpenter then autoscales the nodes in the cluster as well, so that we only pay for the compute we are actively in need of and using.
Your macOS implementation uses Swift and Apple's distributed notification center to detect screen lock events. What are the key technical details that make this work reliably?
Yeah, the app defines two possible states, locked and unlocked, basically the only two things this app cares about. The app creates a listener that waits for specific notifications from macOS. It sets up two observers, which are almost like invisible helpers that watch for two specific events. When the screen gets locked, such as when you step away and it automatically locks, and when the screen gets unlocked, which is when you come back and enter your password. Now, the app reads from a config.json file key details like what AWS access key to use to connect to CloudWatch, the metric namespace and name, and how often to send metrics to AWS. Then, every configurable unit of time, defaulting to 60 seconds, the app ships the current state of the screen lock to CloudWatch. One other configurable parameter in config.json is the machine name. This is configured as a dimension on the metric, which means we can easily aggregate across different machine names, such as the maximum value across the dimension, which would indicate whether any of n machines are unlocked. This could be useful if you own multiple development machines or have multiple developers, each with their own machine.
Now, KEDA, or Kubernetes Event-Driven Autoscaler, is central to your solution. For those who are unfamiliar with KEDA, CNCF project, what makes it special compared to traditional Kubernetes autoscaling?
Yeah, KEDA differs significantly from traditional Kubernetes autoscaling mechanisms in several key ways. First, there's event-driven versus resource-based scaling. Traditional Kubernetes autoscaling relies primarily on resource metrics like CPU and memory usage. The horizontal pod autoscaler scales based on these utilizations. However, KEDA scales based on external events and metrics from various sources like message queues, databases, monitoring systems, and custom metrics. This makes it ideal for event-driven workloads where CPU memory usage are not the bottleneck, meaning they don't correlate well with actual domains. The second way it differs is scale to zero capability. One of KEDA's most distinctive features is its ability to scale deployments down to 0 replicas when there's no work to be done. Traditional HPA can only scale down to a minimum of 1 replica. This zero scaling capability is particularly valuable for things like batch processing jobs, event-driven microservices, cost optimization and development environments, which is primarily what we're speaking about today, and serverless-style workloads on Kubernetes. Finally, the third way it differs is the extensive scalar ecosystem. KEDA provides more than 60 built-in scalars for popular technologies, including message queues like RabbitMQ and Kafka, SQS, databases like Postgres and MySQL and Redis, cloud services like AWS CloudWatch and Azure Monitor, GCP PubSub, or monitoring systems like Prometheus, Datadog, and New Relic. This really eliminates the need to build custom metric adapters for complex integrations.
Now, you mentioned some authentication challenges with KEDA and AWS. What issues did you encounter and how did you solve them?
Yeah, so KEDA has to authenticate to AWS to get access to CloudWatch. And the best pattern for doing this authentication is using the identity of the pod that's running there itself, which AWS can provide in one of two ways. The traditional and legacy way being the Kubernetes service account and OIDC-based IAM role for service accounts. And the newer way being EKS pod identity, which uses an agent running on EKS nodes to annotate and label pods themselves, doing away with the service account linkage. I was inclined toward the latter when I started this project, thinking the latest and greatest would be best. But as I dove into the KEDA documentation, I learned the EKS pod identity approach had been deprecated because the contributors to the source code wanted to reimagine how it was implemented to address some gaps that came up. So I pivoted to use IAM roles for service accounts instead, and that worked for me.
Now let's talk a little bit more about the CloudWatch integration. How does your custom metric work and what does it look like in practice?
Yeah, I wanted to keep the metric as simple as possible, Bart. So I set 0 to locked, 1 to unlocked, and no data, essentially meaning locked because the laptop must be offline. KEDA queries the metric every 60 seconds, but this is configurable in the polling interval field of the KEDA scaled object manifest, which is one of the two types of manifests I had to apply to Kubernetes to get this to work. The example I provided in the article shows the laptop unlocked from 2030 Zulu until about 2100 Zulu, locked from 1800 to 2010 Zulu, and offline from 2010 to 2030 Zulu.
Your configuration includes an interesting detail about supporting multiple developers. How does the solution scale all the way across a team?
For scaling across the whole team, I decided to leverage the dimensions attribute of CloudWatch put metric data payload. AWS's CloudWatch put metric data documentation explains that dimensions further clarify what data the metric collects. In this case, we add just one dimension, indicating the machine name. This allows us to slice and dice for a specific machine name later, or aggregate across a bunch of machine names. We could readily add additional dimensions to the metric, such as team name or office location.
And from a cost perspective, you estimate 80% savings on compute costs. How did you arrive at this number, and what are the actual infrastructure costs of running the solution?
Great question. So my estimated savings depend entirely on the proportion of time the workloads are scaled up. From this assumption, it follows that we can subtract the percentage of time the laptop is unlocked from 100% to get the proportion of time that workloads are scaled down, and thus costs are avoided. Of course, this assumes that all workloads are scaled down with KEDA. If some workloads were left scaled up, we would need to account for the mix of scaled up and scaled down workloads and their compute sizing separately. We should account too for the CloudWatch API costs, though. Per AWS documentation, the get metric data API call is charged at a rate of 1 cent per 1,000 metrics. Since there are 43,800 minutes in a month, and since this configuration fetches the metric once per minute, the configuration would cost about 44 cents per month for each KEDA scaled object in use and fetching CloudWatch metrics. One of the things I'm most passionate about, though, which I haven't tried to quantify yet, is the carbon footprint reductions leading to reduced environmental impact.
Good. Just as a side note to that, just yesterday, I interviewed someone from a startup called Compute Gardener, and I'll send over a link later because if you're interested in the reduced carbon environmental impact, it's something you should definitely check out.
That sounds awesome. Thank you.
Yeah. All right, good. So this is clearly a creative use of KEDA that goes beyond its typical use cases. What other unconventional metrics could developers use to trigger autoscaling?
In general, I like to think about leading indicators of compute demand with the goal of providing just-in-time compute capacity. So it depends a bit on what industry you're in, but in financial services, we could scale on real-time volatility metrics like the VIX fear gauge to right-size trading strategy simulation workloads. In e-commerce, we could look at trends in cart abandonment to scale remarketing activity-centric workloads like recommendation engines and email pipelines. In logistics, we could look at scheduled deliveries over the next day to scale route optimization or inventory ingestion systems. And in retail, we could look at foot traffic to scale CRM systems or loyalty reward processors. I think it really takes some creativity and some insight into your unique industry's needs to decide what metric is best suited for your use case.
You mentioned this is specifically for non-production workloads, accessed via Tailscale VPN. Why is this approach particularly suited for development environments versus production?
Yeah, I mentioned Tailscale to emphasize that this compute does not serve public internet traffic, only private network traffic to my laptop. So a metric derived from activity on my private device could offer a representative sample with which to control the available compute. If that were not the case, we might need to look at alternative data sources, which would be representative of the public behavior, like retail foot traffic or financial services volatility, and so on.
You built this as a launch agent daemon that runs continuously on macOS. What considerations should developers keep in mind when building similar background services?
One of the wonderful things about AWS is they have SDKs for just about every language and just about every platform. Even if that fails, they offer a REST API that you can implement the calls yourself. In this way, I believe this identical service could be built for almost any operating system that supports notification programmatically of the state of the lock screen or user session. More broadly, I would say that implementing the bare minimum of library dependencies needed to do the job and taking other steps to maximize resource efficiency and prevent memory leaks, making sure errors are handled appropriately, such as if you were to lose connectivity on the box, managing secret credentials as securely as possible, and utilizing least privilege when vending out those credentials are all key to success.
Your solution uses Karpenter for node autoscaling alongside KEDA for pod autoscaling. How do these two tools work together to maximize cost savings?
For Karpenter, I used EKS Auto Mode, which I think of as more or less a managed Karpenter cluster. Karpenter is continuously looking at the pods currently scheduled and looking for ways to reduce your total cost. It actually pings the AWS cost API to determine what EC2 instances will best minimize your bill. KEDA sits on top of that and scales the pods themselves up or down. Together, these two components create true elasticity at both the application and infrastructure levels.
Looking at the broader implications, your solution challenges how we think about Kubernetes workload management. What lessons can the Kubernetes community learn from this approach?
It reminds me of an article I had read recently on creativity, which quoted Mark Twain, who said, "Substantially all ideas are secondhand, consciously and unconsciously drawn from a million outside sources." This combinatorial creativity, as scientists call it, can help you innovate your way around problems. This project was no different in my view. I had an idea that I could monitor the state of my laptop, similar to how Prometheus Node Exporter monitors the state of a server, and an idea that Kubernetes could autoscale in response to that metric to save cost. The idea was not new per se, but a new combination of different old ideas. In this way, I'd encourage listeners to question assumptions, think creatively by trying to combine different old ideas in new ways, and consider how that innovation can serve some business or social good. I'd encourage listeners to identify their own patterns of waste and chip away at that, optimize that.
For developers out there inspired by this idea, you've open sourced the code on GitHub. What advice would you give to someone wanting to implement something similar?
I'd start with understanding your actual usage patterns and the drivers to those usage patterns, the signals with predictive value. Can you find the signal or combination of signals that indicates real, upcoming compute demand in your context? Don't be afraid to connect seemingly unrelated systems if you can make it make sense, and monitor actual savings to validate the approach before broader rollout.
Now, what's next for you, Brian?
My wife and I are expecting our first child soon, Bart, so I'm fully expecting life to soon get turned upside down in the best of ways. In between changing diapers, I'm sure you'll be able to find me tinkering on Kubernetes or cloud and hopefully connecting with like-minded folks like you and your listeners.
Fantastic. And for folks out there who'd like to get in touch with you, what's the best way to do so?
LinkedIn's the best way to reach me.
Fantastic. Worked in my case. Thank you so much for joining us today, Brian. Best of luck on your next adventure, and look forward to hearing more about your side projects in the future. Take care.
Thank you, Bart. Bye.